Hey guys, this is our next topic. It is called related rates, and it's basically word problems that involve implicit differentiation. It's a little more complicated than that. There are some things that happen in here where you have to like write equations based on whatever the problem says. So I'm just going to start off, just go straight into an example. So these are the pretty typical. We have a puddle that's shaped like a circle and water is evaporating from it. And so the puddle is shrinking and it's shrinking at a certain rate. They give you a rate. It says the area of the puddle decreases at a rate of 25 pi inches squared per hour. So inches squared is a measure of area and hour is a measure of time. So this is like area per time. We might call this rate because the rate is, you can see the units are area per time. And so we're going to call these rates like d something over d something. And in this case, since it's a rate of area over time, we're going to call this rate dA dt. And you want to think of that as the rate of change of area with respect to time, as in, as time passes, the area changes. In this case, the area changes at 25 pi inches squared per hour. So you want to say 20, it equals 25 pi. I left a little space here because this is a negative rate. And what that means is the area of the puddle decreases. The area is getting smaller. So the rate of change is negative, as in over a given period of time, the area is smaller because the water is evaporating. And then this is pretty typical, assuming the puddle retains its circular shape, at what rate is the radius of the puddle changing when the radius is 10 inches? So what they're asking for is the rate of change of the radius with respect to time. And so I would write that as dr dt. Rate of change of area over change in time. The D kind of stands for change. It stands for, like, delta is usually how we say change, but these are infinitesimal changes. That doesn't matter. The rate of change of area with respect to time, dr dt. That's what we're trying to find. So the general rule here is going to be like, come up with an equation that contains both, in this case, area and radius. That relates area and radius. I don't know why I said both, but don't worry about that. We want to find an equation that we know. We're going to have to come up with this off the top of our heads. And this is the part that sometimes students struggle with. An equation that relates the area of a circle to its radius. And then we're going to take derivatives once we get that equation written down. And you may know that the formula, the equation that tells you the area of a circle is this. A circle equals pi r squared. This has the area in it, which was one of our rates, and this has the radius in it, which was the other thing that was changing. This equation has no dt's in it yet. It will in a second. But the first equation is not going to have dA dt, it's just going to have A. And it's also not going to have dr dt in it, not yet. It's going to have R. And we're going to get the A and the R in there by taking the derivative with respect to time of this whole equation. So I'm looking for dA dt, well, I'm looking for dr dt, but I want my equation to contain both dA dt and dr dt. And so what I'm going to do is I'm going to take the derivative with respect to time of this whole equation, of both sides of this equation. Like we did before with implicit differentiation, we had equations with x's and y's, and we did dy dx. And what happened with those was that dy dx like appeared because of the implicit differentiation, because of the chain rule. So we're going to do that here, but our derivatives with related rates questions are always going to be with respect to time, because rates are always done with respect to time in these problems. This per hour up here tells you that the bottom has to be time, because hour is a measure of time. This tells you that the top inches squared has to be the area, because area is measured in inches squared. The radius, you can guess, the units of that are going to be inches per hour, because a radius is a measure of length, measure of distance, which is measured in this problem in inches. It can be measured in miles or feet or meters or whatever, but in this case, it's inches. In this case, it is inches, so we're going to have inches squared per hour. So now let's take our derivative. This is the part where we have to use implicit differentiation, or the chain rule, as it's often known. And so the derivative with respect to time of a, I don't know what a is. I think it might be a function of time. And I actually know that it is because it's changing with respect to time. As time passes, the puddle gets smaller. So a changes as time changes. So I'm going to have to use implicit differentiation. The derivative with respect to time of a variable is 1 times the derivative of the variable. So this is really equal to 1 times dA dt. Just like if I had the derivative with respect to x, this is what we did with implicit of y. That's like 1 times dy dx. I'm doing that same thing here, but instead of a y, it's an a. So this isn't really that much different from implicit differentiation. It's just that variables are a little different. So I have 1 times dA dt. This is really just dA dt, and normally I wouldn't write the 1. I just wanted you to see like how I used implicit differentiation here to get this. So this is just dA dt, and that's equal to pi, which is a constant. So I'm just going to leave it there. I'm just going to let it sit there in front of my derivative, times the derivative of r squared. And the derivative of something squared is 2 times something times the derivative of the something. So in this case, the something is r. So it's 2 times r, that's the power rule, 2r to the first, just 2r, times the derivative of r, which is dr dt. We also sometimes call this r prime, but I like to use the d over dt notation here so you can see each variable appears. There's r and there's t. Technically, r prime is really something like dr dx, like it was dy dx before, so I don't like to use you shouldn't use the prime notation for these related rates questions, because prime doesn't always mean with respect to time. I wouldn't count on that. So that's why I'm using the dA over dt here, the dr over dt, so we can see all the variables. There's a and there's t and there's r and there's t. Now I have an equation which relates the two rates that I started with. It relates the dA dt and the dr dt. And I'll clean this up a little. It says dA dt, 1 times dA dt. And this is pi times 2 times r, which is really just 2 pi r, times the derivative with respect to time of the radius, times dr dt. And now we're just about home, because this was the thing we were trying to find, right? There it is right there, the thing we were trying to find. And everything else in this equation we know. It says at what rate is the radius of the puddle changing when the radius is 10 inches. So they gave me the r that I want to know, that's 10. And I know that dA dt is negative 25 pi. So I'm just going to fill in all the things that I was given. Negative 25 pi equals 2 times pi times 10, because they said when the radius is 10 inches, if you go back up here, when the radius is 10 inches, times dr dt. And I don't know what dr dt is, but that's okay, because that's the thing I'm trying to find. So I'm just going to solve for this now. 2 times 10 is 20. I can just cross off the pi's. I'm going to divide both sides by pi. And I get negative 25 over 20 equals dr dt. And this, if we simplify it a little, is negative 5 over 4 inches per hour. It's going to be important to me that you guys use the units here so that I know you have some vague idea as to what's actually happening in these problems. So the dr dt, which was the thing I was trying to find, is negative 5/4 inches per hour. And it's good that it's negative. It should be negative because the radius is getting smaller. The puddle is shrinking, so you imagine it's like a circle. It's approximately a circle. It's really more of a cylinder, but we'll worry about that later. It's like a circle. It's sitting on the ground, and as the water evaporates, the circle gets smaller, which means the radius gets smaller. So I'm glad the radius is negative. That worked out well for me. I think in the notes I gave you guys like a whole blank slide if you want to like write more stuff there. There's just sometimes these problems take a little bit of room, so I added some space here. So there's nothing, that's blank on purpose. So that's how we do these. Let's just remember, we write down the things we're given. In this case, it was dA over dt is negative 25 pi. I tend not to write down this r equals 10 at the beginning because you guys tend to like plug it in too early. A good rule of thumb is don't plug in these numbers here until after you take the derivative. You notice I wrote these things down, but I didn't plug anything in until after I took the derivative, right? I took the derivative here, and then I started plugging things in. But if you plug them in too early, everything just turns into 0, and that's not any fun. So we write down the things we're given. We find an equation that relates the rates we were given, or the rate we're looking for, which is dr dt, and the rate we were given, which is -25 pi. And then we take derivatives with respect to time. So if we want to think about like steps, which we can do, this is step 1 right here, writing down the rates both the rate that you're given and the rate that you're looking for. Step 2 is to come up with an equation that relates these rates. That's why they're called related rates problems. Step 3 to take derivatives with respect to time. That's right here, and you can see that conveniently the rate that I was given and the rate that I'm looking for both appeared in that equation. Then the last step is to plug in the numbers we were given and solve for the thing that they were asking for. And if you really want to get particularly particular about this, this is step 5. Make sure that you put in the units so that you like understand what the problem is actually giving you. In this case, it's giving us how fast the radius of the puddle is changing. So this isn't like a super useful application of this, but there are useful applications of this, I promise. We'll get to some of them later. So that's how we do these. I'm going to break this here and maybe do a couple more of these examples, and maybe we'll talk about this. Sometimes sketching a picture is good. So far, these are mostly just kind of standard geometry questions. They ought not to take too long. So keep an eye out for part 2.